Good evening, students. Welcome to my new lecture, that is lecture number 9 on circuit theory series. Today we will continue our discussion on circuit transients. In our last lecture, we have seen that the current response of a RL. In our last class, we have seen that the response of a RL series circuit, unexcited, no source is involved here. Now, the current decays in this manner. I have shown you that the equation of current was A e to the power minus t by tau, okay, where tau is time constant, L by R, okay. Now equal to this one, R by L into T, okay. Now A equal to the current at t equal to 0. Now this will help us in, this will serve two purposes. Number one is, this is the nature of current in an excited L. This is discharging. This is called discharging of L in RL series circuit. Discharging of L means there was an initial current in the inductor. The initial current is what? The initial current is the current at t equal to 0. At t equal to 0, I is A. Let us call it I equal to I0. And I0 stands for initial condition. So, the current decays in the same manner. Here A is I0. Now, this will serve another purpose. The second purpose is, let us talk about a charging of L. Let us talk about charging of L. Before charging of L, let us talk another thing on this. Here VR equal to what? VR is the voltage across the resistance. Voltage across the resistance is I into R. I into R means I equal to I0 e to the power minus t by tau into R. That is I0 R e to the power minus t by tau. Let us call it V0 e to the power t by tau. So VR the nature of VR is same as this one, I0, okay. Now another thing associated with this one, that is voltage across the inductor, VL, voltage across the inductor. We will see how the voltage across the inductor will be in the time of discharging one inductor. We know that VL equal to what? VL equal to L di dt. L di dt, we know I equal to I0 e to the power minus t by tau. So d dt I0 e to the power minus t by tau by tau means r by l, rt by l. So we will get l into I0 and this is minus r by l e to the power minus RT by L. So L and L will be cancelled out. So this is equal to minus I0R e to the power minus t by tau. We know that R by L equal to 1 by tau. So I have written R by L equal to 1 by tau. So this is equal to I0R minus I0R e to the power minus t by tau. Now I0 into R is equal to V0. V0 equal to here I0 into R. So this will be what? Minus V0 e to the power minus t by tau. VL is another decreasing function, exponentially decreasing function. But at t equal to 0, VL equal to what? VL equal to minus V0. So the nature of VL is this type. This is minus V0. At t equal to 0, VL equal to minus V0. And at t equal to infinity, e to the power minus t by tau equal to 0. So VL equal to 0. So this will be the nature of VL, the voltage across the inductor. Okay. Now we will discuss about the phenomena of charging an inductor. So charging of an inductor needs one charging agency. Say the inductor is getting charge from this DC source. So the equation, the governing equation will be this one. If we apply KVL across this loop, we will get VL plus VR equal to V. And we know that VL equal to L di dt and VR equal to R into I, and this is equal to V. So this is one differential equation. This differential equation has two parts. One is CF and another is Phi. And complete solution of I equal to CF plus Phi. We have discussed it earlier. So for CF, we have to solve this differential equation L di dt plus Ri equal to V, equal to 0. Okay, now our main objective is to solve this differential equation. A number of ways are available to solve this differential equation. Now one of the way is we have to determine CF and Phi separately, and for the complete solution of I, we have to add this CF and Phi. Okay, this is one way of solving this equation. Now for CF, we have to solve this equation. Now this is nothing but the natural response of RL series circuit. Now we have seen that the natural response of RL series circuit was like this one, I equal to A e to the power minus RT by L. Okay. Now for Pi we have to solve this equation L di dt plus Ri equal to V and I equal to Cf plus Pi. Now Cf is, we know that Cf is transient response and the transient response will die out with time. So ultimately at t tends to infinity, I equal to only Pi. So the nature of I and V will be the same. Nature of I will be like the forcing function. Now the forcing function is constant one. So Pi will be, the Pi part of I will be one constant one. So let us take I equal to K. This is one constant term. Now, so di dt equal to, we all know that di dt of a constant is equal to 0. Therefore, R into K equal to V. So K equal to V by R. Okay. So I equal to the complete solution of I. The complete solution of I will give us Cf plus Pi, V by R plus A e to the power minus RT by L. Okay. Now in this equation all are known to us. V, R, L, all are known to us except A. So in order to determine this arbitrary constant, we have to apply the initial condition. Say the inductor was initially relaxed. If I0 equal to 0, then put t equal to 0 here. If t equal to 0, then the right hand side will be like this one, V by R plus A. This is equal to I0. I0 is 0. So A equal to what? Minus V by R. So the complete solution of I equal to V by R 1 minus e to the power minus T RT by L. We will write minus T by tau. 1 by tau equal to R by L. Okay. Now this is nothing but one method of solving a differential equation. Let us solve that differential equation another way. The differential equation was L di dt plus Ri was V. Let us take the Laplace transform method of solving the differential equation. Now take Laplace transform in both the sides with I0 equal to 0, initial condition equal to 0. So we will get SL IS plus RIS equal to, this is constant one. So the Laplace transform of the constant term equal to constant term by S. Hence SL plus R into IS equal to V by S. So IS equal to V by S into SL plus R. Okay. Now as one constant term K1 by S plus another constant term K2 by SL plus R. So K1 into SL plus R plus K2 into S equal to what? Equal to V. Therefore, K1 into R plus S into K2 plus K1 into L, this is equal to V. Now, the constant term is K1 into R. In the left hand side, the constant term is K1 into R, and in right hand side, this is equal to V. So, K1 equal to V by R. And the coefficient of S here is K2 plus K1 into L, and coefficient of S here is 0. So, K2 plus K1 into L equal to 0. So, K1 equal to what? K1 equal to minus, K2 equal to minus K1 into L. Now K1, as K1 equal to V by R, so K2 equal to minus L into V by R. Let us put these constants. Let us replace this constant from these two equations. So Is equal to, obviously this is equal to V by R into S plus K2 equal to L into V by R by SL plus R. Okay. Now let us put this as it is, and let us divide both the numerator and denominator of this term by L. So we will get V by R S plus R by L. Now let us take the inverse Laplace transform of this equation, of this term. Now we will get, this is V by R, the inverse Laplace transform of 1 by S equal to 1, and this is V by R e to the power minus RT by L. Now this is V by R 1 minus e to the power minus RT by L. Okay. Now this solution is nothing but the solution we have obtained earlier. Now let us take the third method of solving a differential equation, solving this differential equation. The differential equation was this one, L di dt plus Ri, this was V. So L di dt equal to V minus Ri. Now this is equal to what? This is equal to di by V minus Ri equal to minus V by Ri equal to dt by L. dt by L. Okay. Now let us imagine V minus Ri equal to x. So V by Ri equal to x. So minus R di equal to what? Dx. So di equal to let us multiply minus r in both sides. So minus r pi equal to dx by x equal to minus r by l into dt. Let us integrate both sides. So we will get ln x equal to minus r by l into t plus some constant k, or ln v minus ri equal to minus rl t plus k. Now we have assumed that at t equal to 0, I is equal to 0 or initially relaxed. The inductor is initially relaxed. So if we put t equal to 0 and I equal to 0, we will get k equal to what? K equal to ln v. So let us replace k by ln v. So we will get ln v minus ri equal to what? Minus r by l into t plus ln v. So ln v minus ri minus ln v equal to what? Ln v minus ri by v equal to what? Minus r by l. Let us not carry r by l throughout. So let us replace r by l equal to 1 by tau. Hence v minus ri by v is equal to exponential minus t by tau, or v minus ri equal to v e to the power minus t by tau. So ri is nothing but ri equal to v into 1 minus e to the power minus t by tau, or I equal to v by r e to the power v by r 1 minus e to the power minus t by tau. Okay, so the solution is unique. We got the same solution in all the three methods. So the conclusion is, if we want to charge an inductor by a DC voltage source, we will get the nature of I, this one. Now this is equal to, let us call it I0 1 minus e to the power minus t by tau. Now I0 equal to what? I0 is v by r. V by r means the current when the inductor is shorted. I0 means I0 is v by r equal to the current when the inductor was shorted. Okay. Now this is I0. This I0 is not the, this 0 does not denote that at t equal to 0, I at t equal to 0. This is the final value of I. This is the final value of I, because let us put t equal to 0. If we put t equal to 0, I equal to 0. But if we put t tends to infinity, then I equal to I0 equal to v by r. So the curve of I will be like this one. this is exponentially increasing function, and final value of I is V by R. Okay, this is the nature of I while charging the inductor. And while discharging the inductor, the I was like this one. But while charging the inductor, I is like this one. Now, put t equal to tau or time constant. If t equal to tau, I equal to what? I equal to I0 into 1 minus e to the power minus 1. Now 1 minus e to the power minus 1 means 0.632 I0. So at t equal to tau, the magnitude of I will be 63.2% of the final value. Now let us take this equation, I equal to I0 1 minus e to the power minus t by tau. So di dt will be equal to the rate of change of I. This will be equal to I0, the ddt of 1 will be equal to 0, and this will be I0 by tau e to the power minus t by tau. Okay, so the current will increase as this is equal to positive, so the current will increase. So current is increasing, we have no problem with that. Now the rate of increase is also a time dependent function. The rate of increase is not a constant. Now di dt at t equal to 0, or initial rate of rise of current equal to what? I0 by tau. Now if this is maintained, then time taken by the current to reach its final value will equal to I0 by tau. This is equal to tau or time constant, but the rate is not maintained, so okay, this is the initial rate of rise. If this was maintained, then at t equal to tau, the current should be equal to I0, but this is not maintained. So the magnitude of current at t equal to tau equal to 0.632 I0. I have just written it again and draw it again, where at the time of charging an inductor, the expression of current will be I0, I equal to I0 1 into 1 minus e to the power minus t by tau, where I0 equal to V by R and tau equal to time constant L by R. Therefore, the voltage across the resistance will be equal to Ri. Ri equal to I0 R into I0 1 minus e to the power minus t by tau, or this is I0 into R is V 1 minus e to the power minus t by tau. So the nature of I and VR will be same. So if we plot VR against t, we will get the same nature of waveform, and final value is equal to V. Now we want to determine the expression of the voltage across the inductor, or VL. We know that VL equal to L di dt. and I is equal to what? I is equal to I0 1 minus e to the power minus t by tau. Hence VL equal to L I0 into 1 by tau e to the power minus t by tau. Now L I0 is equal to L I0 by tau equal to L I0 tau is L by R, L into R, so L and L will be cancelled out, e to the power minus t by tau. R into I0, R into I0 is, we know that R into I0 is V, e to the power minus t by tau. So the nature of the waveform of VL is like this one. The voltage across the inductor will decay and the voltage across the resistance will increase. Okay? Let us discuss about discharging one capacitor. Now, this is possible only when the capacitor is charged. So, there is a initial voltage across the capacitor. Let us take that is V0. Now, we have to sort this combination of R and C. So, this is same as the natural response of a RC series circuit, as no voltage source or current source is involved here, so the forcing function is equal to 0. So what we get will be the natural response of this circuit. Now let us imagine the current here flowing through both of them is I. So let us apply KVL in this loop. So Ri plus Vc is equal to 0, and we all know that I equal to what? I equal to C dVc dt. So let us replace I here. So RC dVc dt plus Vc is equal to 0. So dVc dt plus Vc by RC is equal to 0. Now this type of, we have to assume Vc is equal to A e to the power st. So dVc dt equal to what? As e to the power st. Let us replace Vc and dVc dt from these two equations. So we will get As e to the power st plus 1 by Rc A e to the power st equal to 0. Okay. Now, so S plus 1 by Rc A e to the power st equal to 0. Now neither A nor e to the power st can be equal to 0. If either of A and or e to the power st is equal to 0, then Vc is equal to the 0. We don't need to solve for Vc. Then therefore S plus 1 by Rc is equal to 0. If S plus 1 by RC is equal to 0, then S equal to minus 1 by RC. S equal to minus 1 by RC, then from our imagination we can say that this one A e to the power Vc equal to A e to the power minus T by RC. Okay, now let us call 1 by RC equal to tau. A e to the power minus T by tau. Here we will prove it later that the time constant of RC series circuit is RC, R into C. Okay. Now at t equal to 0, Vc equal to what? Vc equal to A. Now we have assumed that the initial voltage across the capacitor was V0. Therefore Vc equal to V0 e to the power minus T by tau. So if we want to plot Vc, we will get this sort of waveform. The initial voltage across the capacitor will be this one, V0. Now at t equal to tau, what will happen? Vc equal to Vc at t equal to tau will be V0 e to the power minus 1 for 3679 or 368 V0. So at tau, the voltage across the capacitor will be 0.368 V0. Okay. Now if Vc equal to this one, so current equal to, as Vc equal to this one, so current through the capacitor is equal to C dVc dt. Now this will be equal to I equal to what? I equal to C into V0 by tau. We will get one minus here, e to the power minus T by tau. Okay. Now V0 equal to what? Tau equal to what? Tau equal to RC. Now tau equal to RC. Let us put RC in place of tau. So we will get this is V0 by R minus V0 by R e to the power minus T by tau. Minus of V0 by R, let us call I0 e to the power minus T by tau. So the nature of the waveform of I will be like this one. This is I equal to this, I equal to minus I0. I will start from minus I0. Okay. Minus I0 means the current will flow in the opposite direction. So current will flow from the capacitor to the resistor, instead of from resistor to capacitor. So if I is this one, so VR equal to the voltage across the resistance equal to VR equal to R into I. R into I means minus V0 e to the power minus T by tau. So if we plot VR or voltage across the resistance, we will get this waveform minus V0. The initial value of the voltage across the resistance is minus V0. Okay. and the minus value will decrease gradually, and finally this will be equal to 0. Okay, so let us conclude for today. Thank you.